Weak acid problems. When we solve weak acid and weak base problems, there's a list of steps that we want to go through which will help us to solve these particular types of problems. The first thing we want to do is look at the problem and decide what the major species are that are in the solution, and we should list them before we start. Then we should look at the substances that are present and choose the species that can produce hydrogen ions or protons and write the balanced equations for the reactions that produce those hydrogen ions. Then we're going to use the values for the equilibrium constants for the reactions that we've written, and we're going to decide which equilibrium will be the dominant producer of hydrogen ions. And that's where we're going to start. Now, oftentimes, people don't want to do these first three steps and they just want to jump right into the problem, and then they tend to make mistakes. So these are important pre-steps to solving the problem. Once we decide which problem or which substance we're going to be dealing with, we're going to write an equilibrium expression for the dominant equilibrium. And then we're going to make an ice chart. We're going to list the initial concentrations, we're going to determine what the changes are, and we're going to find the final concentrations. So we're going to substitute the equilibrium concentrations into our expression, and we're going to solve for those equilibrium values. However, these problems tend to be pretty complicated, and oftentimes they require using a quadratic equation. We don't really want to deal so much with math, so what we're going to do is we're going to solve for x in these equilibrium expressions by the easy way. Basically what that means is that since we're looking at weak acids, only a very small percentage of that acid actually ionizes in solution. So x is so small relative to the initial concentration of the acid that it's insignificant. And we don't necessarily have to use it to get the same answer using our significant digits. So what we'll do is we'll assume that the initial concentration of our acid minus x is really equal to the initial concentration of our acid. X is insignificant. Now, that will make the math easier, but when we're done, we want to verify that x is in fact insignificant. And the way we do that is by what's called the 5% rule. And the 5% rule basically says, is x less than 5% of the original acid concentration? If it is, then x is insignificant, and we don't have to use the quadratic equation. We can solve the problem the easy way. Now, if we do run across a problem where x becomes significant, then we would have to go back and solve for x using the quadratic. Once we've solved for x, we can calculate the hydrogen ion concentration, and then from there we can calculate the pH of the solution, and sometimes the problem asks for other things as well, and we can solve for those too. So let's look at a problem. We have a weak acid solution, and we want to calculate the pH of a 0.500 molar aqueous solution of formic acid. Now, it gives us the Ka for formic acid, and it's a pretty small number, which means that formic acid is a weak acid and only a small percentage of it ionizes in water. Alright, so we've recognized that formic acid is a weak acid, so its dissociation lies far to the left or on the reactant side. So we're going to go through our list of steps and solve our problem. Our first step is going to be to list the major species in the solution. So for this particular problem, we have formic acid and we have water. Now, formic acid has a Ka of 1.77 times 10 to the negative 4, and water has a Kw of 1.00 times 10 to the minus 14. So when we look at those two values, we know that our formic acid is going to be the dominant producer of hydrogen ions. So we're going to use formic acid for our problem. Formic acid donation of hydrogen ions will predominate, technically assuming that water's contribution is negligible. So the next thing we're going to do is we're going to write our equilibrium expression for the dominant equilibrium. and that's for our formic acid. So we've got formic acid ionizing into hydrogen ions and formate ions. So our Ka will be the concentration of hydrogen ions at equilibrium times the concentration of formate ions at equilibrium over the concentration of formic acid at equilibrium. Now our next step is going to be to write our ice chart. So we're going to have our formic acid, our hydrogen ion, and our formate ion. We'll write our initial concentrations first, and it tells us that the initial concentration of our formic acid is 0.500 molar. Now there is no hydrogen or formate ion initially based on the problem, so we'll put in zeros. The next thing we put into our ice chart is our change. Now, we don't know what the change is this time, and when we don't know something, we put in x's. So X amount of our formic acid is going to ionize, producing X amount of hydrogen ion and X amount of formate ion. So that means that when we reach equilibrium, we're going to have 0.500 minus X for our formic acid concentration, X and X. We're going to take those values now and we're going to plug them into our equilibrium expression. So we're going to get 1.77 times 10 to the minus 4 equals X times X, which I'm going to write as X squared, over 0.500 minus X. Now we should recognize this as a quadratic equation, which is pretty complicated for us to calculate, and it's not really going to matter in most instances. What we're going to do is we're going to assume that this X is insignificant. And that's going to make our problem much easier to solve, and then we'll just go back afterwards and prove that that X is in fact. So what we have is 1.77 times 10 to the minus 4 equals X squared over 0.500. So we're going to multiply both sides now by 0.500, take the square root of both sides, and that will give us X. So X is going to equal 9.41 times 10 to the negative 3. Now we want to prove that X is insignificant, so we're going to do our 5% rule. So we'll take 9.41 times 10 to the minus 3. We'll divide it by the original concentration, 0.500, and then we'll multiply it by 100 to get our percent. And when we do that, we get 1.88%. That means that only 1.88% of formic acid actually ionizes in solution. That's less than 5%, so X is insignificant. Now, if you wanted to prove that, you could go back up and solve it with the quadratic, but with 3 significant digits, you're still going to get 9.41 times 10 to the minus 3, so that's going to make our problem a little bit easier to solve. Now, we haven't actually solved the problem yet. What we have determined is what the change in our concentrations for our reactants and products are. Now we need to find out what the values are. So for this particular question, all it asks us for is the pH, so we need the hydrogen ion concentration. And when we look at the problem, the hydrogen ion concentration is X, so it's 9.144. Let's fix that. 9.41 times 10 to the negative 3 molar. So to calculate the pH, we're going to take the negative log of 9.41 times 10 to the minus 3, and that's going to give us a pH of 2.03. So our solution is an acidic solution, which makes sense because formic acid is an acid, and our pH is 2.03. So when we solve weak acid problems, we want to go through a number of different steps and follow it like a recipe. You want to list the major species that are in the solution. You want to use the Ka values to decide which is going to be the dominant producer of hydrogen ions. You're going to write the equation for that ionization. Write your Ka expression. Make your ice chart and fill in your values. Solve for X the easy way. Prove that X is insignificant with your 5% rule, and then solve for whatever the problem asks you for. And that will give you those weak acid type problems.